Hello everyone, welcome to topic 9.4, thermodynamic and kinetic control. By the end of this, you should be able to explain in terms of kinetics why a thermodynamically favored reaction might not occur at a measurable rate. So, if the value for Gibbs free energy is negative, we know that this means that the reaction is thermodynamically favorable, so it's spontaneous. However, not all reactions that are thermodynamically favorable occur, or they happen so slow that it's almost like nothing's going on. For example, the reaction for carbon diamond to carbon graphite is thermodynamically favorable at room temperature, right? You go from something super structured in order to something with less. However, we do not observe diamonds turning into graphite even over the course of a lifetime. The diamond allotrope of carbon, which is here, so this is our diamond, and this is graphite, has many strong covalent bonds in a network. It forms a large macrocovalent network solid. For carbon as a diamond, shown in the image on the left that we labeled, to turn into graphite, it would have to break all of these and remake them into a new structure. To do this would require a very high activation energy. Right, so that's kinetics. So it is highly unlikely that it will actually take place. This is an example of a reaction that is thermodynamically favored, but doesn't occur. The kinetics of the reaction are prohibited, right? So the activation's so high that the particles can't get over that activation energy hill. We describe reactions like this as being under kinetic control, which is to say that the kinetics of the reaction determines if a thermodynamically favorable reaction will take place, right? So very high activation energy. So kinetics tells us how fast it occurs, whereas thermodynamics tells us, does it occur at all? Generally, if the thermodynamics predict that the reaction will take place, but the reaction doesn't occur, we can assume that the reaction is under kinetic control. Some reasons that reactions with negative delta G values do not occur may include high activation energies, unfavorable orientations, and high numbers of particles that must collide simultaneously. Remember, activation energy is EA on the energy graph. Unfavorable orientations, this is collision theory, right? So they have to collide not just period, but in the right way for the bonds to break and reform correctly to form products. And then here, this is also, oops, my apologies, tied to collision theory, where they have to collide all together, right? And remember we said back when we were talking about the molecularity of a reaction in Unit 6, where like things where it's just one molecule reacting in a step of the reaction is more likely to happen than one where two have to react with each other, and that those two are much more likely to happen over something where 3 or more molecules have to collide all at once, because you're hoping that all of those moving bodies arrange themselves just right to collide in just the perfect fashion. The more participants you have in that weird dance, the harder it is to get it to happen. So high numbers of particles must collide simultaneously. You have a bunch of people trying to dance with each other, molecules trying to dance with each other, and they got to orient themselves right for like the magic to actually happen. So let's look at some example problems. So consider the following exothermic reaction. So they tell us here, they tell us that this is exothermic. So we know that delta H is less than 0 or is negative. So that helps us a little bit. So what is the sign for delta S? Well, that's not the one I just figured out. Anyways, we see delta S, so that tells me disorder. So I have two gases versus 1 plus 2 is 3. So I have 3 moles of gas on this side and 2 moles of gas on my reactant side. So I know that I have an increase in the moles of gas. So my delta S for this reaction has to be positive because I have a net increase in the amount of moles of gas. So I am able to arrange them in more ways. So then looking at this, what is the sign for delta H? right? It told us it was exothermic, so we know that that is a negative delta H. And then when will delta G be negative? So delta G being negative, right, we know that this is favorable, and this is favorable. And since they are both favorable, delta G will always be favorable or delta G is negative always because that's thermodynamically favorable. And the two terms in our delta G equals delta H minus T delta S will produce, because I have a negative here and this one's positive, so this whole term ends up being negative. I end up always with a negative term, so it's always going to be negative. This reaction does not proceed at room temperature. Can you suggest a change to the conditions that makes a reaction proceed? So there's two that you could suggest. The first is to increase the temperature. The reason for this is for the activation energy. Right? You increase the number of particles able to collide with enough energy. Okay. The other one would be to, now it should always work, right? Use a catalyst. And a catalyst usually decreases the activation energy by providing an alternate pathway, right? So this decreases activation energy. Now we're considering the reverse reaction. So if I flip it around, right, now I'm going from, if we're looking at the sign for S, I'm going from 1 and 2, 3 moles of gas, to 2 moles of gas. That is a decrease in entropy. So this is negative. And if I flip the reaction around, it is no longer exothermic, where energy is a product, but it is endothermic, so my reaction requires energy. In this case, if we look at delta G equal to delta H minus T delta S, T is always going to be positive, so a negative times a negative is a positive number plus another positive number. This is always going to be positive, so it is never going to be negative. Okay, because the two terms are never favorable. So my delta G will not be favorable, so this will be positive always. Okay, the reaction does not proceed at room temperature. Can you suggest a change? Since this is unfavorable, period, this will never happen. Okay, because it's unfavorable, thermodynamically unfavorable. You have to probably couple it, which we'll get into in a future section, couple it with another favorable reaction in order to get this to happen. Okay, now let's look at the we do. The reaction for iron with oxygen to form iron 3 oxide is shown. I want you to pause the video and calculate the delta G for this reaction at 298 Kelvin. Please remember that the equation for this is delta G is equal to delta H minus T delta S. So I want you to pause the video and complete this now. Okay, substituting in for the given values of delta H, delta S, and T, we end up with this. Please note that the energy units do not match, so I'm converting it here where the joules will cancel out and I'm left with kilojoules. So my final answer should be negative 1,486 kilojoules per mole. So that is the answer for this one. That's our delta G. Now we're going to look at B. This reaction is very slow at room temperature, but much faster when you add water to the reaction. Propose a reason for both circumstances. So you're going to explain why it does not happen without water and why it happens with water. Please use pencil, pause the video, and check back in a second. Okay, so without water, the reaction is under kinetic control, maybe because particles may not be colliding enough. With water, We have an alternate pathway possibly because water's acting as a catalyst, or is like providing a way to help the particles collide more frequently. So now we're going to do C, where we sketch an energy diagram that shows both circumstances described in part D. So we have our energy on this side and reaction progress here, so energy. And then our reaction progress. If I could spell. Okay, so we know that the reaction is exothermic, so that means that the products are lower than the reactants. And then we have our general reaction that might have a fairly high activation energy. And then adding the water, we know that that's going to make the reaction happen a little more, so it's going to probably lower that activation energy. And so the reaction proceeds more. So I'm going to label that because labeling graphs is a smart thing. So this is with water. Okay, so then what happens to the value of delta G when the water is added? Well, think about that. Does it adding something that changes how we get there? These are state functions. If we change how we get there, but not where we started, where we end, the state functions, delta G, delta S, delta H, will not change. So nothing happens, right? When we added water, we changed how fast it goes, so we altered its kinetics. But not the thermodynamic favorability, because it was already favorable. Okay, so that completes these notes. Complete the you do questions, check your work, and thank you for tuning in.